Hello everyone, and welcome back to the AI Research Roundup. I'm your host Alex, and today is May 3rd, 2025. We're looking at an interesting ICLR conference paper titled Syntactic and Semantic Control of Large Language Models via Sequential Monte Carlo, published just over 3 months ago on January 22nd. This paper tackles the tricky problem of making large language models generate text that follows specific rules, syntactic and semantic constraints. Their approach uses Sequential Monte Carlo. Okay, so figure 1 here really visualizes their SMC method. On the left, you see how they manage these, quote, particles or partial sequences, applying grammar rules, correcting weights, using those expensive checks, and then resampling the promising ones. The bar charts on the right then clearly show accuracy, improving step by step across tasks like data science and text-to-SQL as each SMC component is added. It really breaks down how the system works and why it's effective. Alright, building on how the SMC works, Table 1 here summarizes the specific tasks and those potential functions they used. Across domains like goal inference, Python, text-to-SQL, and molecules, it shows the efficient checks, like parsers, and the expensive ones, such as plan simulation or error checking. It even gives little examples of the prompts and outputs, grounding the experimental setup we saw visualized earlier. Okay, so moving to the results in Figure 2, these bar charts really drive home the performance benefits. On the left, you can see how full SMC boosts even the smaller llama model on the data science task, getting closer to much larger models like Codex. And then on the right, across all the tasks we saw in the table, full SMC generally matches or even beats importance sampling, but often with significantly fewer particles, highlighting its efficiency. Okay, so this table digs into the numbers a bit more, comparing the different methods across all 4 domains. We start with the base LM score, then see how adding just grammar or grammar plus correction or potentials impacts things. But look at the bottom line. Full SMC, using everything, consistently gets the top scores for goal inference, molecular synthesis, data science, and text-to-SQL. It clearly demonstrates the cumulative benefit of their approach. Okay, and Figure 3 really gets to the why behind those strong performance numbers we just saw. It shows the estimated KL divergence. Basically, how well each algorithm variation approximates that ideal target distribution, the global product of experts. Remember, lower KL values mean a better fit. And consistently across all 4 domains, the full SMC approach, the dark blue bars, achieves significantly lower KL divergence. This suggests it's doing the best job sampling from the desired distribution, explaining its superior performance. So linking that approximation quality back to actual results. Table 6 here breaks down accuracy based on the number of particles used. We see results for 5, 10, and 50 particles across the tasks. Notice how full SMC, the last row in each block, consistently performs well. Importantly, it often achieves top scores with just 10 particles, demonstrating the efficiency gains over methods like importance sampling, which might need more particles to reach similar levels. So wrapping things up, we saw how this SMC approach achieves strong accuracy even with fewer particles, highlighting its efficiency. Overall, the key takeaway is that Sequential Monte Carlo provides a really principled and flexible way to control these large models, guiding them with both simple rules and complex checks during generation. This allows smaller models to punch well above their weight on tough tasks. Alright, that's all for this AI Research Roundup. Thanks for tuning in.